In this video, we are going to fine-tune Llama2 with QLoRA, and we're going to use the Colab free tier for that. So first go to Runtime, go to Change Runtime, and click GPU in the Google Colab, and click Save. The model that I'm going to fine-tune is Llama, and we need to know on what task it was fine-tuned. So the base model Llama was fine-tuned in causal language modeling, and the LoRa model supports fine-tuning of Llama, and this description is given in Hugging Face, which I'll give in the description below. Let me give an overview of what we are going to do in this quick start guide. We are going to perform instruction fine-tuning, for which we need SFT trainer. SFT stands for supervised fine-tuning, which is also instruction fine-tuning, and this is present in the TRL library. SFT trainer takes some parameters. One is the model. We have already seen that we have used the base model, which does a causal LM. So we instantiate an auto model for causal LM class to take the model. And this model has to be quantized, for which we use bits and bytes configuration from the bits and bytes library. And finally, this has to be converted into a PEFT model using a getPEFT_model function. This is the model that is passed to the SFT trainer. The second is the data set. This data set has to be in such a way that there are instructions in it. I will show how it is done. We load the data set using the data set library. Once I take the data set, the data has to be tokenized, and the tokenization scheme to be followed has to be based on the model. For example, the model in which, that is, the tokenizer used in the Llama model is the same tokenizer with which we want to tokenize our dataset, for which we use the auto tokenizer, which automatically uses the correct tokenizer as per the model that we input. We are going to make use of a QLoRA PEFT training, for which we need to give some configurations, and these configurations are found in the PEFT library, and we give it as a LoRa config because we are using the LoRa model in PEFT. We need to pass a lot of training parameters, like the ones we usually pass for deep learning, like the scheduler and the optimizer and the other hyperparameters. That has to be given through the training arguments class, which is again found in transformers. Two more that we will be using are accelerate and torch. One is for distributed training, and the framework on which we work the entire thing is torch. I had a lot of issues with the import error and module not found error, and so I have very specifically given the version which is to be imported so that we can avoid those errors. That is, we pip install datasets, and in torch we install version 1.13.1. In transformers it is 4.30.1, and in accelerate it is 0.21, and install bits and bytes, PEF and TRL. Failing to use the correct version that I have specified might raise an import error as follows. The dataset is in the G drive, and so I'm mounting the Google Drive. The dataset that we take has to be in a JSON-L format. So see that within the curly braces, I have one key, which is text, and then the value as a # human, followed by the text that we want to give, followed by # assistant, followed by the reply that is required for the question. I had already mentioned that it is instruction fine-tuning, so I mentioned what the input and the output should be in my dataset. The dataset that I created is a hypothetical dataset that I created with the help of ChatGPT, and I have given the link to my dataset in GitHub. We need to first load the dataset. So we import load dataset from datasets, and in load dataset we need to specify that it is a JSON file, and then we give the data file which is a JSON file. And do not forget to give split is equal to train. Failing to give this will result in a value error. Display the dataset and see it has one feature called as text and there are 30 rows in it. I need to import torch, and from transformers I import auto model for causal LM to specify the model, and to tokenize I use auto tokenizer, and to quantize I use bits and bytes config. Model that we're going to use is from Hugging Face. So you need to log into Hugging Face, and the model that we're going to take is the Llama2 7B chat HF. You need to first gain access to it from Hugging Face. And when you get access to this, if you click the link that is provided in the Colab notebook, it will direct you to the page where you will be asked to get the access key. And in that, we will also see something called as model details, in which you have to accept the license from Meta also. So remember to perform all this and then continue with the next step. You must be already having the access token from Hugging Face to go to the next step. If not, you can use this link and copy the token from there. If you do not have a token, you can create a new token. From Hugging Face Hub, import login. And when you say login, it asks you for your access key. You can give the access key. And if the token is valid, it allows you to use the model which is in the Hugging Face, which is the fine-tuned for dialog use case HF. Use the same tokenizer as the model. I use auto tokenizer from pre-trained. And if the model is not yet downloaded, I use trust remote code is equal to true, which will automatically download if it is not already downloaded. Tokenization is nothing but converting your input data into a set of IDs, which are input IDs, and also token type IDs. Token type IDs are nothing but specifying whether they are words or punctuation marks, etc. After tokenizing, we need to pad the tokenizer so that all the input are of the same size, and we also specify the end of the token using a end of sequence tokenizer. Now that we have tokenized and padded our input sequences, we need to quantize them. Generally, all the model weights will be of float 32 bits. We need to convert them into 4 bits because we want to use QLoRA, which is specifically a quantized LoRa, which uses 4 bits for the model weights, thereby allowing us to use this fine-tuning on limited hardware. So you need to specify that it has to be a 4-bit precision, and you have to specify that it is an F4 quantization type that we're going to use. And we need to mention that the model should be computed in a float 16 precision for better accuracy. Now that we have the tokenizer, and we have also specified how to quantize, let's take the model and quantize it. So we take the model, which is specified in model name, and we have already informed how the quantization should be done. And if the model is not yet being downloaded, we download it from Hugging Face. To reduce the memory usage, we can also ensure that the cache is set to false. I have the model with me in the quantized form. This model has to be converted into a PEFT model. And since we're going to use the LoRa PEFT technique, we say import LoRa config. And to convert the model that we have into a PEFT model, we need to import get PEFT model. There are 3 main parameters that we need to set. One is the strength of the LoRa adaptation. We have to have a proper value for this. It is usually started from 0.1, and we keep varying this hyperparameter to check what fits our application. Larger values result in overfitting and the dropout rate in the layers, and the rank of the LoRa adaptation matrix. Here it's a lower rank of 64. Now these have to be passed as parameters in LoRa config. And we also need to mention the task type as causal LM. causal LM is nothing but a language model in which we train the model on next word prediction. Convert the base model into a PEFT model by passing the model and the PEFT config. Here it is the LoRa config. Now when we try and print the trainable parameters, we see that the number of trainable parameters has reduced to this value. We need to set all the hyperparameters required for the training. So we say the output directory in which the results should be stored, the batch size, the number of batches to use to accumulate gradients, the optimizer. Paste Adam W32-bit is a specialized optimizer for training LLMs, and how often you want to save the model checkpoint during training, how often to log the training metrics, the learning rate, the max grade norm, the max steps, the warm-up ratio, the scheduler to be used. All these are passed as arguments in the training arguments class. Finally, we pass all this to the SFT trainer, which is found in the TRL library. Let's have the maximum sequence length to be 512. So we pass the model, which is the PEFT model, the training data set. We know that text is the feature field. We pass the tokenizer, the LoRa configuration, the maximum sequence length, and the training arguments. Before proceeding to training, we will convert all the normalization layers in the transformer model to a float 32 precision. This helps us to improve the performance of the model. When we use a GPU, we start training the model. I have used only 100 steps and the final loss that I get is 0.07. You can, of course, continue your training as per your requirement. This training can be done in a parallel manner with the help of the trainer class, in which case we need to take the attribute from trainer.model.module. Else, we can just take it from trainer.module. We have the LoRa configuration of the output fine-tuned model in outputs directory. In the following file, we take LoRa config.from pre-trained and we load the pre-trained LoRa adapter from this directory. And then we apply the getPEFT method and apply the LoRa adapter to the transformer model. Now for inferencing, I give the human input and I specify what output should be got. And I need to first tokenize it on the specified device. And now if you check the number of trainable parameters, it has to be 0. Next, we will generate the text using the PyTorch language model. First, we use the generate function to generate the text from the input IDs. And the maximum number of tokens that you want to generate, it gets given in max new tokens. We get them as IDs. Now let's convert them and decode them into text, for which we use tokenizer.decode. And we also specify that I need to ignore the end of sequence tokens which are used when decoding the text. So this gives me the output as follows. Thanks for watching. If you found this video helpful, please give it a thumbs up. Subscribe to my channel for more valuable content. And don't forget to check out my code in the GitHub repository linked in the description below.